Hey everyone. In this video today, we're going to be talking about simplifying exponential and radical expressions. And we're going to do that through something called exponent laws. Before we keep going though, I want to talk about this objective a little bit just to make sure we're understanding some of the really key terms that you're going to need to understand in order to be successful with this topic. So an exponential expression involves an exponent. So remember how we've talked about how an exponent is when I raise a variable to a power. So like x to the third has an exponent of 3. Okay. And then remember that a radical is something like a square root or a cubed root. So that would be something that looks like this, or something that looks like this. But we have an infinite number of roots that are possible. We talk about square roots and cube roots the most, but you could have a 4th root, a 5th root, a 17th root. And in this sort of circumstance, we are actually going to start talking about those just with these exponent rules. And then the last thing I want to point out is this word expressions. This is a really important word, and some people just sort of get this confused sometimes. An expression sign does not have an equal sign. So an equation sounds sort of like the word equal, right? We see that in the beginning of it, equation. Equations have equal signs. So like if you said x equals 7 minus y, I don't know, that's a random equation, but it's an equation. An expression is just like one side of that equation. It's just some maybe variables, constants with some operations happening there. So an expression could be something like any of these that I wrote up above. Okay, it could be something like 3x squared times y, right? It could be more complicated, but it's important to know that expressions do not have an equal sign, so you are not solving. You are not in any of these problems going to get an answer such as x equals 2 or y equals 5. Like you're not going to get a strict answer. You are just simplifying the expression, so you're taking it to its most basic form. Okay. And with that said, why is this not moving? Doo-doo-doo-doo. Okay, I don't know why that took so long, sorry. With that said, we're going to go ahead and get started. So we're going to talk about a lot of different laws of exponents today. If you went over this in class, then you probably already have the laws in your notes. If not, there are going to be laws listed in the upper right-hand corner of a lot of these screens, and you are going to want to record those in one big column in your notes somewhere. Okay. But first, we're going to look at multiplying two variables that are both raised to a power. So thinking about what exactly an exponent is, like x squared means I have x times itself. It means that I'm multiplying two x's by each other. Okay, that is the same, x times x is the same as x squared. X to the fourth is the same as multiplying x times itself 4 times. So I could write out 4 more x's, 1, 2, 3, 4. And all of these are being multiplied times each other. Well, when I look at this, how many total x's do I have here? I have 1, 2, 3, 4, 5, 6 total x's. So I could simplify that to say x to the 6th power. It's x times itself a total of 6 times. 6 x's multiplied times each other. And if you notice that this number 6 is really just taking the 2 and the 4, because first I had 2 x's times 4 x's, that gives me a total of 6 x's. So to generalize this to a law of exponent, I have x to the m times x to the n, where m and n are two random constants. And that is simplified to x to the m plus n, right? So if I'm multiplying this variable times itself, and both times there is a power, I have to add those powers. Now that we know that law, we're going to do another practice. So here we have x to the 7 times x plus 3. In order to solve this, I know I'm going to have x and then to the sum of 7 plus 3. So I'm adding those two together, and then this is going to come out to equal x to the 10. So I have a total of 10 x's multiplied times each other. Okay, now we're going to move on to the next law, and this law is talking about quotients. So if I'm dividing and then I have exponents, I'm going to show us how to approach this actually in the same way we did the last problem. So let's say I have 7y's. I'm going to write out 7y's here. And the reason I did that is because that represents x to the 7. And then on the bottom, I have y to the 3rd, which means y times itself 3 times. Okay? Well, what we should know by now, and I'm going to write this off to the corner, if I have something in a numerator and a denominator of a fraction, and they're the same as each other, something divided by itself is equal to 1. So we can cross those out. Sort of like I can cross these 2's out here because 2 divided by 2 is 1. Well, y divided by y is also y. So for each y that I have in the top and bottom, I can cross one out. So I'm going to go ahead and I'm going to cross a y out there and there. I'm going to cross a y out there and there. I'm going to cross one out there and there. Okay. Now there's nothing left in the denominator. All I'm left with are the 4 y's in the numerator. And I can rewrite that as y to the 4th, right? 4 y's multiplied times each other. And that is my solution. Well, if you notice the number 4, what happened is I had 7 y's on the top and 3 on the bottom. And I had to take away 3 from the top to take away 3 from the bottom. So essentially, I could rewrite this as y to the 7 minus 3 power. Okay? Because I took the 7 here and the 3 there, and I took 3 away from the bottom, and I took 3 away from the top. So that means that I can generalize this law to x to the power of m minus n, where I take the exponent on the top and I subtract it from the exponent on the bottom. Or in other words, in math terms, where I subtract the exponent from the numerator minus the exponent from the denominator. Moving on to an example of this, we're going to follow that law, and I'm going to take b and take 12 minus 8 as the exponent, which gives me b to the 4th power. Okay, for this next rule, we're going to talk about raising an exponent to another power. So we can see 2 exponents here. You have b squared, and then that's all in parentheses, and it's being raised again to the 3rd power. So what this is telling me is I have b squared times itself 3 times. Okay, and when I do that, I've sort of rewritten it like the original multiplication rule we talked about, where now I have 2b's, 2b's, 2b's. Well, if I add all those 2's together, that gives me a total of 6b's. Okay. Well, if you notice, this 6 comes from me taking 2 3 times, which means 2 times 3. So if I have this in the form x to the m times x to the m raised to the n power, that becomes x to the m times n power. If I'm raising to an exponent, then I multiply. Okay. And then here, we're going to do a quick example. So since we have y to the 3rd to the 4th, I have to raise this to the 3 times 4 power, which gives me y to the 12. Now we're going to talk about negative exponents. So a negative exponent is sort of hard to conceptualize, but basically, when I have a negative exponent, I have to do the reciprocal, but I make the exponent positive. So if I'm going from a to the negative 5, that becomes 1 over a to the 5. Basically, I switch which part of the fraction this term is in. So essentially what I had was I had a to the negative 5 over 1. What I had to do is bring the a to the negative 5 down to the bottom, and then that makes the exponent positive. Okay? And we do this because we want to express things in terms of positive exponents. And that means that x to the negative m is written as 1 over x to the n. Here we have y to the negative third. Once again, I write that by putting this in the denominator of the fraction, but making the exponent positive. So that gives us 1 over y to the third. I do want to point out one other thing. So actually, let me change colors here. Let's say I gave you 1 over y to the negative third. In the first example, I told you that I bring the term down to the bottom of a fraction, or I bring this down to the denominator of a fraction. But what really matters is that I'm switching. So if it starts in the numerator, I bring it to the denominator. That's what I did here. But if it starts, a negative exponent starts in the denominator, like it does here, what I do is I bring it to the numerator. So really, that would become y to the third. Okay, and you could say y to the third over 1, but y to the third over 1 is the same as y to the third. So that's just to show you with the negative exponent, you take it to whichever part of the fraction it's not in, and then you make the exponent positive. Okay. The next rule is something raised to the 0 power. Okay. And so when you have something raised to the 0 power, a lot of people want to say this is 0 because anything times 0 is 0, but that is not actually the case here. Okay. So, when we talked about something like y squared, I said that that was y times itself, right? But there's also sort of an imaginary one out front, right? 1 times y is the same as just y times y. Well, if I have y to the 0, I don't have anything in terms of multiplying y's. There's no y at all. But I still have essentially that 1 out in front, right? There's no like y times y after that. That's not a thing. It's just 1. For that reason, anytime I raise something to the 0th power, my answer is 1. I don't care what you're raising to the 0th power, the answer is always 1. So, in this case, I have c to the 0. What is my answer? My answer is 1. Here, I have 1,987,364 to the 0th power. Huge, huge, huge number. But it is to the 0th power, so it literally doesn't matter how big that number is. My answer? 1. So, anything raised to the 0th power is going to give me 1. Okay. Now we have a little bit of practice. So here I have an x and a y. So I have two variables being multiplied times each other, and then I have it being raised to a power on the outside of those parentheses. So if I have terms that are being multiplied or divided, so if there's addition or subtraction, this does not hold true. But if it's just like multiplication or division, so in this case, multiplication of two variables, or if there's a coefficient in there, the power essentially just gets distributed to both of those terms. Again, this only works if this is multiplication or division, but because of that, this 4 essentially distributes to both of these terms. That will give me x to the 4 times y to the 4. Okay. And so, when I take this term, x times y to the m, that simplifies to x to the m times y to the m. Right? That exponent distributes to both the x and the y. Now another example of that. Again, that 3 applies to the a and the b, so I have a to the third times b to the third. Okay. And just like I said before, I said if you have terms that are multiplied or divided and you raise them to an exponent, the exponent applies to every one of those individual terms. The same applies here. So I have b divided by c, and that whole quantity is raised to the third power. So I have to take each of those terms inside parentheses and raise each individually to the third power. And that gives me b to the third over c to the third. So when I'm writing this for the generalization here, that becomes x to the m over y to the m, because again, I have to apply that exponent of m to each term inside the parentheses. And for another example of that, I'm going to come here. That 5, that exponent, has to apply to both the x and the y that are being divided. So this gives me x to the 5 over y to the 5. Now we're going to talk about fractional exponents. So if you have an exponent that is a fraction, what that really means is that you have a radical on your hands. And that is why the instructions here say rewrite in radical form. So basically, if you have a fraction in your exponent, the denominator is really a root. So whatever number is in the denominator, you're going to take that and you're going to put that in the little corner of a radical sign. So that is a root. So I have the square root of x and then to the first power. The numerator, this stays an exponent. The denominator is a radical. Or more specifically, it is a root because it is the second root, but it indicates that there is a radical, the radical being this symbol here. Okay, so I wrote it like this, but the square root, we don't have to write that too. We normally don't. We also don't have to write the first power, because why would I write x to the first power? That's the same as x. Look how much prettier this answer is. So, as I write that as a rule, I'm going to say whatever the denominator is, it is going to be the nth root of x. Okay, so if this was like 1/5, it would be the 5th root of x. If it were 1/7, it would be the 7th root of x, etc. In this case, I have x to the 1/3. This is another really common root, the third root. So again, I take that denominator and I turn that into the root of the radical, and now I have the cubed root of x, or the third root of x. Okay, and I didn't write any exponent here because remember the numerator is your exponent, but I don't need to bother writing an exponent of 1. Okay, here I'm showing another example because now the numerator has a number that is not 1. So the denominator here, the 3, that still becomes my root. So I have the third root of x. But I also have this 4 right here. Okay, and again, I said that 4 stays an exponent, so I write that here. The 4 stays an exponent. If you're wondering, I did write that under the radical symbol. That is the same thing as writing this, right? It's the same thing as raising the third root of x to the 4th power. But I think that this tends to look a little simpler, a little prettier, so that's how you're going to see me writing it. Okay, and then we're going to do another example here. Again, we have the 5 is the root, the denominator is always the root, and then I have the 2 as an exponent, so I write an exponent of 2, and we're left with the 5th root of x squared. Okay, now we're going to go backwards. So if I have the square root of x, remember when I said that the root, like this is a 2, it's an imaginary 2 because it's square root, the root is always the denominator of the exponent. So I don't have an exponent written here. So I have an x. My numerator is just the exponent that would be here. That's a 1. It's an imaginary 1 because it's not written, but it's there. So 1 over, and then I take the root and I make that the denominator. So the square root of x, another way to write that is x to the 1/2 power. Okay. And then if we're going to generalize that rule for an exponent law, when I have the nth root of x, that's the same as x to the 1 over n. Okay, so you can see how this is just backwards of the law we did like 2 slides ago. We said x to the 1 over n is the nth root of x, and we said the denominator, that always becomes the root. Well, here, the root becomes the denominator of the exponent. So it's the same law, actually, just in a different order. So looking here at the cubed root of x, we're going to have x. Again, there's no exponent currently being written, so I have a 1. And the radical, or the root, the 3, becomes the denominator of my exponent. So I have x to the 1/3. Now I have a little more complicated problem. I have the square root of x cubed. Please remember, again, if you see this symbol, the radical symbol, and there is no number, that is a square root. It is the most common root that we use, so we don't even have to write the 2. But sometimes when simplifying exponents, it can be easy to write it in because that helps us remember what exactly the root that's there is. So when I write this in exponential form, I need to take the x to the 3rd, but now I have to take the 2, and instead of being written as the root, I write it as the denominator of the exponent. And that gives me x to the 3/2. Now I'm going to try one more time. Here I have x to the squared, x to the 2nd power x squared. My root is 3, so I'm going to divide my exponent by 3. And we have x to the 2/3. Okay, now we're going to have a couple slightly more complicated problems, but we're done learning the rules. So I'm going to put some things together. Let's say you see a problem and you have 2 different variables here. I have an a and a b. I am going to work through this, and I am going to start with the a's, sort of put them together. And if there were multiple terms with b, I would put those together too, but there's only one with b. So I'm going to start by looking at these 2 terms with a, and I have a squared over a. So I have to think, how would I simplify a squared over a? Well, this is a quotient, or a division, so that becomes a to the 2 minus 1, right? Because the a on the bottom, there's only one a. And when there's a quotient, I do subtraction in the exponent. And then I have that times b to the negative 3. So if I keep working this out with looking at the a term first, I now have a to the 2 minus 1. Well, that's just a to the 1, or a. And then I have b to the negative 3. Well, remember, a negative exponent means I'm going to take that term, put it in the denominator, but make the exponent positive. So I'm going to rewrite this, but I'm going to bring b to the 3 down to the denominator, and now all of a sudden it has been made positive. So that whole term simplified is a divided by b cubed. Let's look at another one. I have a couple of terms that are with the variable a and a couple with the variable b. So again, I'm going to look at those separate. Both of these are quotients, right? I have an a over an a. So as I simplify this, I'm going to take a to the negative 2 minus 2, and then I'm going to multiply that times b to the 3 minus 2. When I do those subtractions, I come up with a to the negative 4 times b to the 1, or just b. And once again, one of these has a negative exponent. So I'm not simplified until the negative exponent is gone. And that means I'm going to take b, and then I take a to the 4, I move it to the denominator, and that has made it positive. So I have b over a to the 4. Okay, here, this one, I only have one x and one y. The y is there, the x is there, but the x has a negative exponent. So again, I want to get rid of a negative exponent. So y squared just stays. X to the negative third, we bring that down to the denominator, and we make it positive. Right. Here, this one might look a little trickier. You see fraction and you see a cubed root. The key here is to convert that cube root, that radical, into exponential form first. So this is equal to x stays on the top, and then I think, what is the cube root of x equal to? I'm going to take that 3 and make it the denominator of the exponent. So the cube root is x to the 1/3. Well, now that I have an exponent, I can just follow the normal quotient rule, which is to subtract the exponent from the numerator minus the denominator. So this is really x to the 1, right? Just 1x. So when I simplify that, it becomes x to the 1 minus 1/3, subtracting those exponents, and that comes out to x to the 2/3. And then we have one more question. This is the last one we're going to do. We'll see. This is one that has powers raised to another power. So you can see this whole term on the inside being raised to the second power. So remember, each individual term inside the parentheses needs to be raised to that second power. So I'm going to write this out. And first, that 3 needs to be raised to the second power. Next, x squared needs to be raised to the second power. And that's x squared times 2. And then y cubed needs to be raised to the second power. So that becomes y to the 3 times 2. And if I simplify this out, 3 squared, that'll give me 9. X squared times 2 gives me x to the 4, because I add those two exponents. And then here we have y to the 3 times 2, that gives me y to the 6. Okay. Awesome. We're done going through examples, but I do want to point something out, and something that might be confusing you. And you've seen that in this problem, that when I raise to a power, I'm multiplying exponents, whereas when I'm multiplying, I'm adding. And sometimes this can be just a little bit tricky to remember what the difference for all of them are. So I'm going to remind us of our rules again. And if I have x to the m times x to the n, that becomes x to the m plus n. If I have x to the m to the n, I have x to the m times n. So there is a trick in remembering these rules, which is basically, look here on the left. Right here, I see a multiplication. And a multiplication results in an addition. Then down here, I have an exponent, and that results in a multiplication. So if you think about it, think about how addition is the most simple. Multiplication is the next most simple, and then you have raising to an exponent. Okay? That's sort of in the order of least to most complicated. Basically what you're doing with these rules is you're taking a step down. So if you're presented with a multiplication, you're taking it one step simpler and you're moving to an addition. If you're presented with an exponent, you're taking it one step simpler and you're performing a multiplication. So hopefully that's helpful. The same thing kind of works with division and subtraction, right? If I were dividing exponents, we learned that that is subtraction. You're always just doing one operation simpler. Okay. So that's the trick that I use to remember it. Hopefully that's helpful for you. If you're able to memorize it without using that trick, then good on you. You have a better memory than me, but that is great. But yeah, that is basically it for this video. So I hope you understood everything. And if you have questions, as always, go ahead and let me know.